All right, let's get right into it. Today, we're diving deep into one of the most vital life safety systems in any building, the fire pump. Look, this is about way more than just pushing water around. It's about engineering absolute certainty when it matters most. So let's jump in.
Just think about it for a second. In a fire, water pressure is everything. It's life. When a sprinkler finally pops or a firefighter needs water now, they are counting on that pressure being there. It's the thin line between a minor incident and a full-blown catastrophe. So for us, the big question is always, how do we engineer a system that delivers without fail every single time?
To even begin to answer that, we've got to start with the fundamentals. So first up, we're going to break the whole system down into its core components. Think of this as meeting the team. Every single player has a critical job to do.
Okay, so here are the key players in our 3D model. Right at the heart of it all, you have the main pump. That's the powerhouse. And right alongside it is its smaller partner, the jockey pump. The controller panel, that's the brains of the whole operation, making all the decisions. Then you've got the plumbing. Water comes in through the suction manifold and gets blasted out the discharge manifold. And of course, for testing and safety, you have a test header and a relief valve to make sure things don't get out of hand.
Now, and this is absolutely critical, you're not just pulling these designs out of thin air. Every single decision, from pipe size to pump selection, is governed by a super strict set of rules. We're talking about heavy hitters like NFPA 20, the gold standard for fire pumps, plus local codes like the Saudi Building Code 801, and even client-specific standards like those from Aramco. These codes aren't suggestions, they are the blueprint for safety.
Let's zoom in on what I like to call the system's unsung hero, the jockey pump. I call it the pressure guardian, because its whole job, day in and day out, is to keep the system primed and ready to go at a moment's notice.
You see, the main fire pump is a beast. You definitely don't want that thing kicking on just because of a tiny, inevitable pressure drop from a small leak somewhere in the system. That's exactly where the jockey pump steps in. It's a small, low-flow pump whose only mission is to handle those minor pressure losses, keeping the system topped off and ready without putting needless wear and tear on the main event.
So how do you set it up correctly? Well, it all comes down to a really simple pressure pecking order. The jockey pump has to be set to shut off at a pressure that's at least 10 psi higher than the main pump's churn pressure. And churn pressure is just the maximum pressure the main pump can create when it's running with zero flow. That little 10 psi buffer is the magic that ensures the jockey pump always takes care of the small stuff first.
Sizing 1 is actually a pretty straightforward 4-step recipe. First up, you've got your main pump's flow rate in GPM. Next, you calculate the jockey's flow to be just 1 to 3% of that, nice and small. Third, you grab the main pump's churn pressure right off its performance curve. And finally, you just add 10 psi to that number to get your jockey pressure setting. That's it. Simple, logical, and it works.
Okay, let's talk about the big one, the main pump itself. And really, the first major decision you have to make is what's going to power this thing. This choice between diesel and electric has huge ripple effects across the entire design.
And what's so interesting here is the really clear trade-off you have to make. I mean, electric pumps are awesome. They're incredibly reliable, they're quieter, and they need less maintenance. But their big Achilles heel is that they depend on the power grid. If the power goes out in a fire, so does your pump. Diesel pumps, on the other hand, are totally self-sufficient. They bring their own power source. But that freedom comes with baggage. You need a fuel tank, serious ventilation for exhaust, battery chargers, the whole shebang.
And this is a perfect example of where the rulebook can basically make the decision for you. In a lot of places, especially those following Saudi, Royal Commission, or Aramco standards, the rule is crystal clear. If you can't guarantee a reliable backup power source for an electric pump, you must use a diesel pump. It's mandatory because reliability is just not negotiable. So, you've picked your pump. Awesome! But how do you actually know it's going to perform when you need it most? That's where we need to decode the pump's performance curve. You can think of this as the pump's final exam, and the test itself is written by NFPA 20.
Every single certified fire pump has to hit 3 non-negotiable performance points. First is the churn point, that max pressure at zero flow we talked about. Second is the rated point, which is basically its day job. And third, and you could argue this is the most important, is the overload point, which proves it can handle the absolute worst-case scenario.
The test starts right at its rated point. This is its core promise. The pump has to deliver 100% of its rated flow at 100% of its rated pressure. No excuses. This is the baseline.
But here's the thing. A real fire doesn't care about baselines. As more and more sprinklers open up, the demand for water just skyrockets.
so the test pushes the pump way past its comfort zone, demanding it deliver a massive 150% of its rated flow.
And this is the crucial safety net. While it's pushing all that extra water, the pressure is not allowed to drop below 65% of its rating. Why? This is the rule that guarantees that even the sprinkler head at the very end of the longest pipe run, the one furthest from the pump, still has enough juice to actually fight the fire. It's a safety margin that literally saves lives.
Okay, theory is great, but let's get practical. We've covered the parts, the sizing, the power, and the performance tests. Now, let's put it all together and look at the physical layout of the pump room and then walk through a real-world calculation.
You know, how the water gets to the pump is just as important as how it gets out. NFPA 20 is super strict about this. For example, any eccentric reducers have to be installed with the flat side up. This prevents nasty air pockets from forming that could literally starve the pump of water. You also need a perfectly straight section of pipe, at least 10 times the pipe's diameter, leading right into the pump. No elbows allowed. These little details make a huge difference.
And the room itself is a key part of the safety system. It's basically a bunker for the pump. Codes in places like Saudi Arabia are very specific. It has to be a dedicated room, surrounded by fire-rated walls. You need clear access all around the equipment for maintenance, plus good ventilation and emergency lighting. I mean, it makes sense, right? The pump has to survive the fire long enough to fight it.
Okay, let's connect all the dots with some real numbers. Let's say our hydraulic calcs tell us we need 1,000 GPM at 110 PSI. Boom, that's our main pump rating. From there, we size our jockey flow. We'll use 1.5%, which gives us 15 GPM. Then, the jockey pressure is just 10 PSI higher, so 120 PSI. And finally, we do our overload sanity check. At 150% flow, the pressure has to stay above 65% of 110, which is 71.5 PSI. See? It's a logical cascade, from the initial demand right down to the final verification.
So, we've walked through the components, the codes, the calcs, everything that goes into engineering certainty. From that tiny jockey pump setting to the way the suction pipe is laid out, we've seen how every single detail matters. Which brings me to a final question for you. Now that you've seen all these rules, what's the #1 thing you're going to double check on your